My name is Marcino Paolo. I happen to be director of this institute, and my job today is to provide you welcome speech for Dream Chemistry Award of 2022. This is very special competition because it recognizes young researchers who want to dream to solve some fundamental problems related to chemistry and some other branches of science. And what differs this competition from the others is they don't have to bother with the budget, they don't have to bother with risk assessment. Just use your imagination and logics and of course your scientific experience. This year we had about 50 people who were nominated to this competition, but only 5 of them passed to the finals. And I would like to welcome them. First of all, I would like to welcome Guillaume Fentom, Karl Brozek, Liang Feng, Claudia Contini, and Ahmed Badran. They are coming from really top scientific institutions of Europe and United States. I would like also to welcome a scientific committee. These 18 people, they have to do the job, they have to select, and I know that selection was very difficult. And among them, I would like to welcome Professor Pavel Jungwirth, who is responsible for the Czech edition of this competition, because this year we moved from Prague to Warsaw. And they actually joined this competition in 2017, but this Dream Chemistry Award competition was actually invented by Robert Howist in 2013, who convinced directors of this institute. Actually, he was director at that time, so it was very easy. Now you have to pay to start this competition. Luckily, in 2017, he made agreement with the Institute of Organic Chemistry and Biochemistry, because they are not only excellent scientists, but they are also very rich. So. I also welcome Jason Moran, who is a winner of the last competition from 2021, and he will deliver a lecture tomorrow for all of us. And I would like also to mention the honorary committee. If you have such a competition, you need some really top world scientists. They will say, okay, this is a very good idea, and they are not present here, but I would mention their names. As a Nobel Prize winner, Richard Schrock, Józef Michl, Krzysztof Matyjaszewski, and Bartosz Grzybowski. So I'm very happy to have all of you here. I'm also happy that we can meet again offline. I hope everybody is vaccinated at least 3 times, and fingers crossed for the candidates. Thank you very much.
It's a great pleasure to welcome you on this festival of scientific dreaming. And I could not resist to ask you one question. Who of you has a scientific dream? Raise your hands up. Guys, my experience tells me that if you do have a scientific dream, it's 80% of the success in science. And then, if you persist to your dream, you will never grow old in science. You will always feel young. So I wish you success. I wish actually to follow the dream. The path is important, not the goal, the final goal, just to follow it. And finally, I would like to say that this contest, you cannot apply. you have to be nominated. It was actually the idea of George Whitesides. He said, if it is a serious contest, it should be like a Nobel Prize. It should be nominated. And this year, 2 Nobel Prize winners nominated the candidates, and one got in and one almost got in. And last but not least, it's not a competition. It's a festival of scientific dreaming, and it's my great pleasure to ask the first speaker, there's Ghislaine Van Tom, who will tell us something about the brain.
It's my great pleasure to be here today. I'm very happy, and I would like to thank the organizing committee for giving me this opportunity. I feel really honored. And so today I would like to tell you something about my dream, how supramolecular materials could be used for the next computing paradigm. Let me tell you first something about the computers nowadays. Computers have shown extraordinary abilities. For example, they can recognize faces on your phone and classify your friends and family. They can recognize your speech. They can also recognize your handwriting. Nowadays, cars can drive themselves, and that is thanks to amazing computer programs. And the computer programs such as AlphaGo have managed an incredible achievement in 2016, that he was able to defeat human player at the strategic game Go. And that was really a breakthrough, because for that, the computer had to learn aspects of human intuition. And that was really an important step. But then we can ask the question, what is the energy cost to achieve this computation? Well, energy consumption in computers is a challenge. Let me give you some numbers. When you do a Google search, this is the equivalent of the energy needed to light a bulb for 17 seconds. That may seem negligible, but when you bring it to all the amount of Google search we do all together in a year, that is actually a very large, huge number of energy. And that is nowadays a challenge because of the energy crisis that we encounter here, particularly in Europe, with the price of energy increasing. And so it's clear that this is a challenge we like to tackle. And so to improve the efficiency of our computers, let's compare it to the brain. On one hand here, I show the supercomputer. The supercomputer can achieve a number of 10 to the power 18 operations per second, and this requires an energy of 21 megawatts. This is the supercomputer Frontier that you can find in the United States, and it's the best one at the moment in the world. This, to give you an idea, is the equivalence of the power needed to fuel about 10,000 households. Now, what about the brain? The brain can achieve about 10 to the power 16 operations per second. This is what you need to operate your body, to recognize, to think, and to at the same time. And this requires about 10 to 20 watts of energy. That is the equivalent of the energy needed to power your computer, your laptop. As you can see, there is a large difference between the way how the supercomputer use energy compared to the brain. So to bottom line, the message here is that the brain uses 100,000 times less energy than the computer. And so the idea that if our computers could mimic the function of the brain, perhaps we could reduce this number. And so why is the brain so remarkable? Well, although the brain remains a mystery, neuroscientists tell us that its incredible ability comes to 3 factors. First is the vast connection that you will find in the brain. Second is the hierarchical structure. The brain is composed of neurons that you can see here. These are the computer units of your brain. And they exchange information through synapses. Here, these red balls, the synapse. These are the memory units of your brain. And these synapses, their strength can be increased when you learn, or they can be decreased when you forget. And our brain is composed of billions of these neurons and trillions of these synapses. And the third factor that makes our brain so remarkable is this time-dependent function. is that the neurons can exchange information through short pulses of electricity. These are called spikes. And these spikes, we have about 10 quadrillion, it's 10 to the power 24 of these spikes of electricity going through neurons per second. So that is what makes the brain truly efficient. Now, how does a computer work compared to the brain? Well, computer work with what we call a von Neumann architecture. You feed your computer with a binary input, and you get a binary output. It goes through a central processes unit, and this has to exchange data with the memory. And this central unit has to work very hard to keep the data moving back and forth with the memory unit. And so there is this point here called the bottleneck, because you have the data that needs to move sequentially through this point. And that is highly energy inefficient. So this is rigid. On the other side, you have the neural network that can exchange information in parallel within this network. And this is dynamic. It can rewire itself based on the training and the learning. And that makes it highly energy efficient.
Dzień dobry. Dziękuję za zaproszenie. That's all the Polish I know. I was practicing it for about a week. I hope it made some sense. Good morning. Thank you so much for being here. I'm really excited to tell you about a dream that I've had for a long time, figuring out how to control the chaos within a chemical system as a way to get that chemical system to capture and store energy. In particular, I want to approach entropy, the concept of entropy, something that a lot of chemists ignore. It's that thing that you're like, you kind of have an understanding of what it means in your reaction, but you kind of ignore it. I want to embrace entropy as a chemical design strategy so that we can make materials that can actually accomplish this goal. In general, my long-term vision, while I'm still alive as a chemist, is to be able to address all of the challenges facing green and sustainable energy by using this approach of how do we control entropy. Everything from carbon capture to water dissociation. How do we use water as a source of hydrogen, a clean source of energy? But today I'm going to focus particularly on how do we control the disorder-order change, the entropy in a material, to capture waste thermal energy all around us in better thermoelectric materials. And how do we use this same principle to design better batteries, and with particular focus on how to control what those electrodes can do. Okay, so I want to give you a little bit of a roadmap. First, I need to tell you what I even mean by entropy, because even though this is a room full of chemists, this is not just for the people watching on YouTube, it's a lot of us don't really know how to begin to develop an intuition for what entropy really means. And then I need to tell you why it's actually the change in entropy that matters when we're trying to capture energy. And then from there, I can tell you about my dream of how using that understanding, by being able to change the entropy of a system, how we can use that to capture thermal energy and store that energy in better batteries, okay? So let's start with a familiar example. You try to heat water on your stove. You're making tea, or you're trying to cook pasta, or whatever, and you can turn that flame up as hot as it can go, and it's going to take a very long time to start to boil the water. And even when it's boiling, it's going to take a really long time to evaporate all that water. This is why you can cook a soup all day and you don't lose all the water, right? So where is all that energy going? Why does it take so long? Why doesn't it just immediately evaporate when you start to heat water? Well, to explore this, in preparation of today, I did an experiment in my house, and I took a paper cup. This is in my house, in my garage, and like a good American, I could go to the hardware store and buy a flamethrower. So this is an actual flamethrower. It costs about $50, which is remarkable. No one checked, did a background check or anything. I bought this thing, and so this is the paper cup. Right before I started to burn it, so I started to burn the paper cup. It burns really well, and almost instantly, it's gone. Okay. So let's repeat that experiment, except now I put water in that cup. So I start to try to burn it, and it turns out a little bit of it will burn, and the only part that will burn is the part of the paper cup that isn't touching water. And I was getting frustrated, so I held that flame right at that cup, okay? And in the end, the cup stands. The water's all in there too. So where's all that energy going? Well, we have to return to chemistry. We have to take a molecular perspective to understand what's going on here. If you were to see water in that cup, and you take a snapshot, you would see something that looks like this. You know, water molecules are constantly dancing around each other. And when they dance around each other, they form these hydrogen bonds. But this is just a representation of what a little portion of water might look like in that cup. So you start to heat the water, and what you're going to do first is you're going to break those hydrogen bonds because they're really weak. They barely even last even when you're not heating, because the water molecules are constantly dancing around, and the water will simply, as you heat it, simply just adopt a new configuration. And you can keep trying to do this. You take that flamethrower and you keep heating the water, and it's just going to adopt a new configuration, and a new configuration, and another configuration. The fact that water is able to reconfigure itself into so many nearly indistinguishable configurations is the first example we'll talk about today of why water has so much entropy in it. Okay, so let's take another perspective. Many of you have, I don't know what chemistry textbooks are like in Poland, but in the US, when we try to teach students what entropy is, we give them this comparison. We have a very clean, tidy bedroom, and then we have a messy bedroom. Entropy, so the textbook will typically say there's very low entropy and very high entropy. This is completely wrong. Neither of these are really telling you about how much entropy you have. These are really just two possible states that a bedroom could be in. Really, the highest entropy, the most likely state of your bedroom is probably the way that your bedrooms look right now, I'm assuming. Probably pretty neat, but a couple things are out of order. And there are lots of ways for your bedroom to look that way, mostly in order, but maybe a couple things are messy, okay? And so really, what entropy is one way to think about it, it's missing information. Okay, what do I mean by that? Well, you take two dice, and you roll them, and you add up the numbers that you get. The number you will get is probably going to be 7. Sometimes you'll get 2, sometimes you'll get 5 or 6 or something. And if I asked you, you said, okay, so let's say I told you I rolled and they added up to 7. And I say, okay, guess, what was the identity of the two dice? You're going to have a really hard time guessing correctly because there's so many configurations that give you that same result, okay? It's also why 7 is the most likely outcome, because there's so many different configurations that all really give you the same result. It gets even more remarkable the more dice you use. If you were to do this with 10 dice, the most probable sum that you would get would be 35. Now, if I asked you to guess the identity of each of the die, there's like no chance that you'd be able to do that because there's so many configurations to give you the same result, okay? We can go even farther. 100 dice, the most common sum is 350. Now, as it turns out, there are 10 to the 77 ways for those dice to land on the table or the floor or whatever. Huge number of ways. But more than 10 to the 76 of those ways will add up to 350. Now, try guessing the identity of all of the dice if I told you it added up to 350. And to really bring it back to chemistry, imagine we're working with 10 to the 23 dice. And that's about the number of molecules of water in a cup of water. So this gives us a perspective of molecules have a tremendous number of ways to configure themselves. And all of those different ways, you may not really be able to distinguish from a macroscopic observation, but that's really the essence of entropy. It's the amount of missing information because of all of the configurations that exist in the system, okay? So Another way of thinking about it, let's get a little bit more abstract. Let's say I give you 4 circles, and I say one of them's going to be blue, but 3 are going to be yellow. Guess the arrangement that I pick. Well, you're going to have a hard time because there are 4 ways to do it. It's even harder if I introduce more circles. There's going to be more ways to arrange them. More degrees of freedom gives more equivalent ways of distributing into different configurations. And get more complicated. Let's say I have not 1 row, but 4 rows at a time. Or rather than 1 blue circle per row, 2 blue circles, or any number, or any color. You introduce more degrees of freedom, you introduce more available ways of arranging things. And this is getting at the next important concept for us. It's that each of these different things that I drew here, each of these different systems had different amounts of entropy, okay? And so it's really this idea that different systems can have different amounts of missing information, differences in the unknownness between 2 different systems is really what's going to allow us to design chemical systems that can capture and store energy. And so that's the dream. Let's use delta S to make new materials that can capture energy.
It's my great honor to be here and to get into the Dream Chemistry Award top 5. It's really a great pity that I cannot participate this event in person, but I really feel grateful to have this opportunity to give this presentation online. So today's my presentation title is to introduce to you my dream chemistry of building active artificial molecular factories. And I hope that I can utilize this new design, the hierarchical and complex materials and chemistry to utilize it to solve the problems related to climate, to also the energy related issues. So firstly, I want to give you some big pictures of my dream projects, right? I think everyone still remember the past 2020 summer, extremely hot, not only in the United States, but also around the world. It generates record-breaking temperature in many spaces, and many other frequencies that we see the water level decrease, we see the historic drought, and also the wildfire around the world. That is very serious climate issues generated by this climate change. And right now, we have very serious issues related to the CO2 concentration in the atmosphere. As you can see from the figure presented on this slide, right now we have reached a record high concentration of the CO2 in the past 800 years. They reached around 400 ppm. And research has shown that this significant increase in concentration in the CO2 has a very close correlation with the fossil fuel burning. Therefore, the current policy wants to replace these fossil fuels with renewable clean energy, right? Utilize wind or electricity or solar power to replace the traditional fossil fuels so that we can slow down the increase of CO2 in the atmosphere. While those technologies, they can only slow down the increase of the CO2 concentration in the atmosphere, but they cannot reduce the concentration or decrease the concentration of the CO2. So to do that, to keep the global warming below 1.5 degrees Celsius, we have to develop a new technology like the carbon removal technology to remove the current carbon budget in the air so that we can slow down the global warming below 1.5 degrees Celsius. So that is something I'm really interested in to remove the CO2. So right now, because of the human activity increase, also the carbon capture problems by the natural world, the biological world, is not efficient at all. So we need to develop the carbon capture technology to help us to remove those CO2 and convert it into one important fuels to maintain the sustainable carbon cycle. And a lot of new startup companies and industries, they are interested in those areas. As you can see, the huge amount of money investigated in those new areas. And many countries in the world have this net zero commitment, right, to achieve the collective carbon emission by the end of 2050 or by the end of 2060. That is the goal of our global mission. And also, I think speaking of the companies, worldwide, many companies, they are committed to achieve these net zero goals. And also the percentage is increasing rapidly. However, the problem is that many companies, they claim that they can plant trees and save the forest to achieve this net zero goals. However, if we want to achieve the net zero by planting trees, we need to plant more than 4,000 times of trees we have now, and we basically do not have enough space on the earth. That's why I think chemistry is extremely important in tackling these huge problems. We need practical applications of the materials and also the chemistry to tackle those problems in the carbon capture problem, and also the utilization of those carbon dioxide and convert it into the very useful fuels in the future.
Nice to meet you, everyone, and many thanks for this great opportunity to present my chemistry dream at this peculiar event. And so in my first slide, I decided to add an image of a star taken with the Webb's telescope. Now, I don't know anything about astronomy, but this is a chemistry dream festival, and every time that I dream, I look up at the stars and I start to wonder. And even the lullaby that I sing to my daughter before she starts to dream at night starts with "Twinkle, twinkle, little star, how I wonder what you are." Well, I will tell her soon enough that actually science can answer those wonders and can tell us exactly what the stars are and how beautiful they look. So with this star that I want to guide you through my chemistry dream. So nature, it's our primary source of inspiration. We are constantly inspired by nature and we are constantly fascinated about it. And one of the main reasons why we are so fascinated, it's not only because it's beautiful, but it's also because it can be quite complex and we don't fully understand it. So nature remains our primary source of inspiration, and we are constantly observing it and trying to reproduce it. And this is an example of what I mean. So on the left-hand side, there is the painting of my father, of Cala Gorizier, and on the right-hand side, there is the actual Cala Gorizier in Sardinia. And what my father was doing was spending hours and hours to reproduce something that was already in front of his eyes, something that was already surrounding him. And why this choice? Well, because it's only when we try to reproduce nature, we can actually appreciate every single detail, and we can appreciate its complexity, and we can actually, in the remaking, we can actually understand the nature a little bit more. Another example of mimicking nature, maybe for something less abstract, more practical, is given by George de Mestral, that in 1940 was every day was taking his dog Milka for a walk. And what he discovered, well, what he observed actually, probably all of us observed the same, but is that some plant seed were attaching to its clothes and to Milka fur. And what he did, differently from us, because this actually happened to me and to my dog, but I never thought to take actually those seeds and look at them up under the microscope and see what was going on. And what he understood is that these seeds were attaching to the fur in a sort of hook and loop modality. And what he did soon after is to create what we use in everyday, the Velcro. So this is a classic example of biological, natural observation translated into creating a bio-inspired system that can be useful for any everyday activity. And but scientists nowadays can create amazing things, taking inspiration from nature. They can create artificial hearts, artificial insects, artificial hands, and also they mimic some biological function like the motility. And this is actually the focus of my chemistry dream as well. And but this is not a new trend in science. Scientists have been trying to mimic nature from centuries, and an example is Leonardo da Vinci, that about 500 years ago, he was trying to study nature, so the structure of birds, and understand how that structure could lead to motion, and was translating this biological observation into engineering tool that will allow the man flying for the first time. Now, over the years, science evolved, and we passed from the ornithopter to the Antonov, the world's largest aircraft. And in this evolution of science, we actually learn how to perform better than nature. In fact, in a normal flight, for example, a London-Warsaw flight, we are already flying 3 times faster than the bird with the greatest airspeed velocity. And this evolution of science led to new ways of locomotion. It changed our life in a way that before was completely unthinkable. So in the same way, in my chemistry dream, what I aim is to take inspiration. I cannot fit an Antonov in my lab, so I'm working more in the micro and nanoscale. And what I do is observing how biological cells move in order to create a motile artificial cell.
Thank you, Pavel and Robert, for the invitation to come and be here again. It's my pleasure, of course, to be included in this competition and tell you a little bit about, this time, a new dream, and one that I've actually been thinking about for the better part of a decade. So this is actually a really important problem. It's one that's, I think, near and dear to a lot of people that think about biology and some of the important problems that we're trying to address in the world today. So I don't have to belabor this point, but climate change is a major issue, right? So Lang gave us a really fantastic primer on all the impacts that climate change is having today. And this is largely, of course, or at least is correlated with the significant amount of carbon dioxide that we as a species are pumping into the atmosphere. Now, over time, and since the beginning of the Industrial Revolution, this amount of carbon dioxide has been steadily on the rise. And despite significant policy changes by many nations in the world, a number of other economies continue to rely on burning of fossil fuels. And as such, these numbers are likely continuing to increase in the near future. Of course, maybe I can stand over here. Of course, this has had pretty significant consequences on the health of our planet. And so just to illustrate this, and I'm not going to belabor these points too much since we're all familiar with some of these impacts, but the rising temperatures of the planet as a function of the increased carbon dioxide in the atmosphere has resulted in the melting of the significant fractions of the polar ice caps, which has resulted in increased sea levels that is predicted to decimate coastal populations over the next few decades. It also has resulted in an increase in the frequency of natural disasters that happen all over the world. And these can often be incredibly unpredictable, but have rising tolls that must be really addressed by the countries in which these disasters occur. And so you can see in the US, the percentage of the GDP that of this country, of the US alone, that's devoted to being able to address natural disasters as a function of climate change continues to increase. Now, one of the other areas that only recently has become clear as a byproduct of climate change, and this is actually really important for my lab's work where we're trying to develop new antibiotics, is that the increase in the global temperature has actually incentivized greater degrees of transfer of genetic information between microbes. And much of this genetic information is in the form of antibiotic resistance genes. And so there has been a very drastic and strong correlation between the increase in the temperature of our planet and the resilience of many antibiotic-resistant bacteria in the clinic and also in nature. And so there's been a significant push to really try to address many of these issues, importantly and probably largely through policy changes by most countries on the planet to be able to draw down the amount of carbon dioxide that exists in the atmosphere. And this is largely through policy changes that are expected to, over time, reduce the amount of carbon dioxide in the atmosphere. And so there are a number of graphs that you may have seen that look like this that really seek to predict what might happen if these policy changes were in fact carried out. And what you can see is that in most cases, especially for the current policies that are in play, the carbon dioxide that is already in the atmosphere will continue to remain there for many, many years, if not decades. And because of the consequence that this has on the planet, many of the deleterious impacts of climate change will continue to be there and perhaps even get exacerbated to the point where it might actually reach a point of no return. And so there's been a significant motivation in trying to follow pathways where not only are there policy changes that are meant to enforce a reduction or perhaps completely eliminate the amount of carbon dioxide that we put in the atmosphere, but rather develop so-called carbon negative or negative emission technologies that pull or draw down carbon dioxide directly from the atmosphere.